Can you all hear me? Cool. What? I was told to wait till 35 after by the guy. What? So who here this is their first SCaLE? Any first SCaLE attending? You like it?
Love it.
The swag alone is worth the admission. Anybody else? It's all good? You like it? You gonna go next year? You gonna go next year? Are you gonna go next year?
Probably.
I heard a rumor it may not be here. We're getting too big.
This proximity to the airport's really nice for me.
Yeah.
When you say here, you mean here LA or here? There's a nice convention center in San Diego.
Oh, that's where those Comic-Con people go. They used to go. Oh, that's true. So I'm going to start if the guy doesn't show up. But. I know. I'm listening to the band. Should I go? I'm going to go. I was supposed to read something, though, he said. I'm going to go. Hey, everybody, what's up? Welcome to my talk. Thank you for going to SCaLE. This is good. You're the dedicated group that goes to... Who's been here the whole 4 days? This is a dedicated group. Okay, I'll ask that. Who's been here for all 13 SCaLEs? Oh, okay. Figured you'd want to ask that. I don't have a prize for you, but that's pretty awesome. I have no way to verify that, so I'm trusting you. Do you really? That's awesome. This one. All right, so what I'm going to talk today is I'm going to go over what is real-time processing. I'm going to talk about what the Raspberry Pi is for those that don't know. And then I'm going to combine the two. So like, okay, now we know about real-time processing, and now we know about the Raspberry Pi. Can the Raspberry Pi do real-time processing? And why the heck would you want to? And then I'm going to talk about an example project that that could be incorporated, real-time could be incorporated in the Raspberry Pi. And then we'll open up for questions. So what is real-time processing? And it's the application that requires a guaranteed response within strict timing constraints. The key word of that sentence is guaranteed. As we'll go later, it's not running fast. So here's some examples of real-time processing. On the upper right, you have the F-22. I'm kind of familiar with the real-time processing on that one. There's lots of real-time processing. There's Asimo. It's built by Honda. I'm not sure why Honda is building robots, but he built the robot. And the motor controls, especially that particular robot walks. And if anybody's done robotics and try to mimic bipedal walking movement, it's very complex. Oh, okay. Well, then they need to drive cars. That makes sense. Car. That's a picture of my car. No, it's not. There's tons of real-time processing nowadays. It's just amazing how much computing power is just in a normal. I mean, obviously that's a VAT, the C7, but even the budget-minded car nowadays has tons of real-time processing in it. And that picture, it's a little bit dark. That's actually a nuclear reactor. So you could imagine there's lots of real-time timing constraints and things you must do with a nuclear reactor to prevent bad things from happening. So I think sometimes people get confused because they say, oh, real-time processing. And there's two types. There's hard real-time processing and there's soft real-time processing. So hard real-time processing is basically if you do not meet your timing constraints, something bad really happens. With soft real-time, system will be degraded, but, yeah. So here's an example of hard real-time. If you're doing it's called the GNC, the guidance, navigation, and control of a rocket. I mean, obviously, a rocket during launch, there's a very high dynamic things going on, and you have to respond within milliseconds, if not sooner. Because if you don't, that happens. And that one is a picture of the inaugural flight of the Ariane 5 rocket. Very short maiden flight of the Ariane 5 rocket. They actually did self-destruct it. There was lots of things that went wrong with the software. One of them is they said, oh, we have the Ariane 4 software, let's just port it to the Ariane 5. And even though this is 16-bit and the other one's 32-bit and 64-bit, we could just do the conversions, and lots of bad things happen, and because of it. Now here's the most controversial picture of SCaLE. Yes, I have a picture of an evil iPod. That's very evil because it's anti-free. But it's the perfect example I could think of to demonstrate soft real-time requirements, especially the click wheel. So if you're writing, the evil Apple developer in Cupertino, he's writing the software to control the click wheel. If the software is running too slow and it's not getting the interrupts and it's having latency issues, the user will get mad, but the iPod will still work. You may go, oh, I wanted that song. No, not that song. The other song. No, the one before it. And they'll get frustrated and they'll throw it against the wall. But the software will still work fine. So that's an example of soft real-time. So what is real-time not? And this is my personal pet peeve. It is not software that runs really, really fast. I have an example. Let's say I have a thread that has to execute a certain amount of processing every 2.5 milliseconds. It's 2.5 milliseconds fast. That's pretty fast, right? But let's say you have a system that only supports 5 milliseconds. It ain't gonna work. And a little side story. I was interviewing a person for my job. I work for a defense contractor person. And I was interviewing her, and if you have an interview with me, the projects I work on are very, very strict, hard, real-time kind of things, all of which I can't talk about. And I asked her, what is your experience with real-time application development? And she said, tons. I'm kind of looking through the resume. It's like, well, it's not obvious. Where have you done real-time processing? Maybe you've done stuff at home or something. She goes, oh, no, I write software really, really fast. And I'm kind of like, oh, okay, I was kind of curious. I was like, well, define fast. She goes, oh, it's seconds. I was like, seconds is not fast. So eventually, with some other questions, it was sort of, we'll call you, don't call us. But no, it is not. There is a bigger misconception. It is not software runs really fast. Again, when we talked about the definition, it is software that, it's basically you are guaranteed to meet your timing requirements. Real time could actually be quite slow, but it has to be guaranteed. You have to be guaranteed that your software is going to run within those timing requirements. And the other one, it is just because something's embedded, it is not real time. So real quick, when we talk about metrics, we have interrupt latency. So the time that the software responds to an interrupt, that's called interrupt latency. So let's say you have something that's driving an interrupt, an external clock that does like a 5 millisecond pulse, and your software can't respond to that. The latency is 25 milliseconds before it sees the first pulse. That's no good. And also scheduling latency, that's a whole talk in itself. But essentially, real-time applications have a real-time scheduler, and as I was talking about earlier, let's say you have a task that has to run every 2.5 milliseconds, the hardware and the OS has to wake up that task, have it do its processing, and then release it. And that's called schedule latency. So what's the Raspberry Pi? I was at the SCaLE, or I belong to the SVG Lugs, SVG Hack. I think I recognize a couple of you, and we had a bunch of Raspberry Pis out, and I was amazed that some people actually never seen one before. So who doesn't know about a Raspberry Pi? It's okay, you can raise your hand. So Raspberry Pi is a really cool device. It was originally intended for education. It is a very cheap computer. So it's an ARM-based. It's an older ARM. It is single core because they wanted a lower cost. Although I think the new one is a quad core, and it's the ARM 7, right? Yeah. So they've improved it. Yeah. But so that's cool they improved it. But the standard stock one that's been out forever. It's running at 700 megahertz, single core Atom. You could have up to 512 megabytes of memory. There's ones that have 256. And it's all for around 25 bucks. So essentially for $25 you have a standalone nice little computer. And even though it was originally intended for educational purposes because it was cheap, they want to put cheap computers in the classroom. It's because it's so flexible, a ton of people are using projects on it. So what is good about the Raspberry Pi? Well, like I said, it's cheap. It is easily hackable. We like that. It comes with GPIO pins for input-output of devices. And it supports 1080p. And that's actually one of the things that's very popular with Raspberry Pi is run XBMC on it. Is anybody running XBMC on their Pi? Yeah. And it's just amazing I have one at home and it plays my high def, legally obtained high definition. Yeah, well, just in case, this is being streamed. Don't know who's watching. Here's some examples of some Raspberry Pi projects. There's a bunch of them. You Google them. There's billions of them out there. But the one on the far left is a internet radio device to do streaming of internet radio. The one in the middle, he was actually using it for time-lapse photography, and he even has it on motor control, so he could actually move the camera as doing time-lapse. And the other one that's very popular with the Pi is that you can run a thing called MAME. Everybody, who doesn't know MAME? For those that don't know MAME, it's basically an emulator where you could emulate your old video games, again, for the ROMs that you have legally obtained. Yeah, and so this one here, that's actually a cool device. I am jealous of the one on the far right. They built this nice cabinet case and with a LCD display, and so they basically made a tabletop. Actually, it's Donkey Kong. But with MAME, if you just load the ROMs you have. So what's so bad about it? This thing's so cool. What's so bad about it? Well, it doesn't have a real-time clock. Because again, they wanted a lower cost. So if you just had a Raspberry Pi and you powered it on and you weren't connected to the intertubes, it wouldn't know what time it is. And we'll get into a sense, there's different distributions out there, but all the kernels that come with it are not Linux real-time kernels. So that guarantee stuff that I was talking about earlier, it can't guarantee it. The RAM can't be expanded, at least not easily, as far as I know. So it's the RAM is built onto the computer itself. So it's not like you can go fries and throw it in some DIMM memory. The bus that controls everything is really kind of slow. And it turns out the network interface control card that's built in is actually kind of an internal USB controller or USB NIC. So basically, your network controller and anything you have connected to all the USBs that you have share the same bus. Depending on what you have connected to it, this could get kind of slow. And especially the early ones had a bunch of power issues. I think if I remember right, there was a little bit of a hardware feature. It was a bug, it was a feature, I guess, where you had to supply good power. And if you don't, then you start having like reboot issues. Or you'll plug in, especially the early ones, you'd plug in your USB keyboard because you want to use your new Raspberry Pi, and the keyboard wouldn't work. So I think that's been mostly resolved, but you basically, if you're going to get Raspberry Pi, get yourself a really good power supply for it. So the question is, the reason for this talk, can the Raspberry Pi, this little device, do real-time processing, and why the heck would you want to? Well, it can with a lot of tweaking. As we mentioned, the kernel it doesn't usually come stock with a real-time kernel. Again, this is not a surprise. This is not a knock. It's supposed to be a general-purpose computer. It's not supposed to be dedicated. When you come with a distro, it comes with a bunch of stuff because they want you to do a bunch of stuff. So they want you to do like web processing and web hosting and doing sound and doing all this other cool stuff. But if you're going to do a dedicated project, all that stuff gets in the way because all that stuff steals your CPU time. And I think I talked about it doesn't have a real-time clock. But because it's cheap and because it's flexible and because you're talking about education, to teach kids how to build like robotics and do their own things, something that's unfortunately very lacking nowadays, that would be an awesome thing. And it's also sort of the hacker mentality. And I talk about the old-fashioned hacker where you get something that it normally wouldn't do and you change it so it can. I'm not talking about the hackers that steal your credit cards and sell it for Bitcoin. So let's say we all have Raspberry Pis, and we all want to do some real-timey kind of stuff, and we're going to do a project. How are we going to do it? So for our example, or my example, we're going to make a a tank with a Nerf cannon. So this thing has to be kind of complex, right? First, it has to detect the baddie. Then it has to move the turret to the point to the baddie. Then it has to know, hey, I'm pointing to my turret is in the right spot, and if the baddie's moving, I got to lead the target. So it has to calculate the position of where the target needs to be. It needs to send the signal saying, yes, fire now. And it has to do all that stuff and not hit anything while it's doing it. Now, we could be kind of lazy. We could say it can only fire when it's not moving, but that's boring. That's kind of lame. So let's say this thing's going to fire on the fly. It's going to go wherever direction it's going, and it's going to point its turret while it's moving, and it's going to kill the baddie and fire the super deadly Nerf dart. So as we're going to get into this is kind of like, this is kind of multi-threaded, right? There's lots of different tasks going on. So let's first talk about the real-time clock because that's the easiest thing to solve. So you could buy, there's tons of them out there. There's Adafruit sells one. There's others. Get on eBay. You could buy a real-time clock and connect it to the GPIO pins. What's that going to give you? Not only do you know the time, but now you have some accuracy in your processing. Yeah. Well, hold that thought. So now we have a clock. So it's like, well, that's cool, but we need a certain driver we're going to get into, because the Raspberry Pi doesn't do good pulse generation. So let's just say we have a couple motors on our tank. We have the drive motor, we have the motor that's controlling the turret. And even if you have a stepper motor, you have a really good stepper motor, they require very accurate pulses. right? So it's going to, and the reason why this is important is, let's say we want to move the turret a certain direction. We want to move it from here to here. Well, we got to tell the motor, okay, you're here, you need to go this far, this amount of time. And if the pulses aren't exactly right, you're going to get some slop. And what's going to happen, we're going to miss the baddie. And the baddie's going to kill us. Another thing is, let's say we have, on the other end of the tank, we have a sensor that's going to detect walls in front of us. So let's say we detect an object, we go, okay, it's 3 feet away, we're going to motor go this far, but no further, and then stop, because we don't want to hit the object. Well, again, that's all a command to the motor, and if you're off, then you're either going to be too short or probably too long. Now, I've actually seen some Raspberry Pi. I was doing some Google searches for this talk, where people were using Raspberry Pi for kind of that sort of thing, and what they did, they ran into this issue. And so what they did, they just made their, like this one guy had like this dune buggy kind of thing. He just made it stronger. He's like, look, I know I'm going to hit things, so I'm just going to make it really, really strong so when I hit it, it doesn't break. But there's a more elegant solution to that. And then there's a couple of things you could do. So Adafruit sells actually a servo hat that plugs on top of the Raspberry Pi, and that will do all the processing for you. I did mention Adafruit a couple times. This is not a commercial. I don't work for them. I buy a lot of stuff from them. So if you're watching Adafruit, you know, a little karma coming my way would be good. The second thing you can do is the 9850 pulse generator. This guy actually has a very accurate clock, and it'll generate pulses. That's sort of what you're talking about. And I'll talk about that in a sec. Here's some pictures. This is actually the Adafruit. Again, not the bias Adafruit. You know, if you can find one out there, but that is available for you. And you can see it's controlling like 4 motors in that example. And the one on the right, that's the 8950. So for the second one, the 9850, what I did was I bought one really cheap on eBay. I think it was like $3. I could have got it cheaper if I bought it in bulk. So you connect it to the GPIO pins. And then what I did is I wrote an ISR, internet service routine, to basically trigger on that GPIO. And it was very, very accurate. I actually hooked up to an oscilloscope to look at the pulses coming out and then I had some debug software to see how the Raspberry Pi was responding to it. And remember I was talking about that interrupt latency earlier? It was very, very low. So that was good. So problem number 3. So we have a real-time clock, which is good. We have our pulses. We generate nice, steady stream pulses to our motor controls. This is good. The third problem is, remember I was talking about all that stuff we got to do? Well, you're going to require some different processing threads kind of running at the same time. Now, some people may think, oh, I'm just going to write one big, long-ass program that's going to do everything all at once and serially, but that never works. So what we need to do is we need to create different threads. So what we need is we need a scheduler. We need the operating system to launch our threads. We need our threads to do their processing and go away, because a lot of those threads are going to be accessing shared resources. And what we don't want is thread number 1, let's say accessing something on the USB bus and not releasing it, and here comes thread number 2, it needs to grab something on the bus, whatever it is, and it can't because it's having a resource collision. So basically we need something to process our threads and clean them up. And as I said, the default distributions don't cut it. There are solutions though, hence this talk. There's a thing called RTMS, which I'll talk about in a sec. You can build your own real-time kernel, but who the heck does that anymore? Who does make menu config? You do?
Yeah.
You are hardcore, sir, and so are you. When was the last time you did make menu config? Friday. You, sir, I have respect for you. I've gotten lazy. Oh, yeah. I mean, well, hey, look, and besides, you know, before you judge me, I actually started on Slackware 4.3, and I needed a SCSI driver, and I actually had to desolder something on a SCSI card to actually get it to work, but I've gotten lazy. So you could, if you know, if you want, you could build your real-time kernel, or if you don't want to do that, you could say, well, you can remove a bunch of stuff that we're not going to use, and maybe you might get away with it. Remember I was talking, so priority inversion. Priority inversion is essentially something that has a lower priority task blocking a high priority task. So let's say the F20, I don't want to do that one. So let's say you have a very high priority task that has to do something super quick, and you have something that's super slow. So usually it's like processing is your more high priority task, and your user displays are lower priority tasks. So let's say a user task is blocking your very high priority task from processing your flight controls. That would be bad. A fun example of priority inversion is this guy. This is the Mars Pathfinder. It was several missions ago. It wasn't the Curiosity, it wasn't the rover, it wasn't the Spirit Curiosity, it was the one before that. It landed safely, and everybody was happy at JPL. And then all of a sudden the next day, they couldn't talk to it anymore. And it was basically because of a classic priority inversion. Luckily, they were able to fix the software, and they were able to recover the mission, and it was very, very successful. But you really have to be careful about priority inversion. I mentioned RTMS. This was actually really cool. It is a free, open source, free as in beer, free as in freedom, real-time operating system. Pardon me, the only equivalent I could think of is there's a commercial one called Wind River VxWorks, and I've used both. I use a lot of VxWorks. I've run a little bit of RTMS, and it is very equivalent. It's a very powerful real-time operating system that's been ported to Raspberry Pi. To be honest, not all the stuff works with it. So you may have some networking issues and all that stuff, but all the core stuff works with it. And it's used, NASA uses it, it's used for medical, there's a wide variety of uses. And you could download it. You could just you could just go in your Google and search RTMS and Raspberry Pi, and you could port it over. And you will have an honest-to-God, preemptive real-time operating system, which is cool. And it's free. Free as in beer, free as in freedom. And we all love that. So one of the things we could do is, if you don't want to go the RTMS route, or you can't because you need to use the functionality that's not working with it, and you don't want to build your real-time kernel, well, what can you do? Well, you could overclock the CPU, and the CPU is easily overclocked. There's something called RASB config that you get when you get a Raspberry Pi to configure your hardware, and you could do some overclocking. It's a little bit of a fuzzy magic kind of a thing. So, yeah. RTMS, as far as I know, does not support overclocking yet. So that's something that I've been wanting to work on, but my real life has been affecting that. But that's why I didn't list it. But you do that. Also, remove anything you're not using. So, for instance, in our take example, we're going to do a bunch of stuff. We're not going to use FTP, probably. So get rid of it. You're going to have all bunch of network daemons, and if you're not going to have your tank connected to the network, get rid of all of those daemons, because what are they doing? They're stealing clock resources away from you. I can't think of a couple others. What you could do is just take a look at the services. Anything that's not there, get rid of. It's not ideal, but you might get away with it, especially if you have the other modifications that we've made. So in summary, we've talked about what real-time means. Hopefully you guys have a better understanding of that. It's, like I said, it's sort of my pet peeve when I see stuff on the net and I have interviews and people don't understand what real-time is. Just because I just deal with it every day. It's just, yeah, it is what it is. We talked about things you could do with the Raspberry Pi. We talked about the pros and cons. It is actually a very cool device. I highly encourage you to get one and start hacking on it, because the more people that are hacking on it, the better the community grows. And we talked about my Nerf take example. Actually, hopefully for next SCaLE, it will be at the SVG Lug, SVG Hack booth that we're going to have, and you can say, Steve, where's that Nerf tank that you were talking about last year? I'm like, here it is. And with that, actually, I'm a little bit early, but does anybody have any questions? Yes, sir.
When you suggest using many configs to build the real-time kernel, what's exactly?
That is a separate talk. There, basically, anything you're not using, kill it. Just disable it. Well, actually, no. So there are. God, it's been a while since I did this. Yeah, there's a bunch of flags that you need to set exactly for the preemption. Yeah, there are. I think I had something a couple years ago, or I had to do this. I was actually doing an audio application, so I needed a real-time kernel, and I Googled how to do it, and it was quite involved, but. Because everything you have to set certain things a certain way. That is true. Right. Because remember, if you're going to do a real-time kernel, you're going. The reason why the stock kernel doesn't support this is the stock kernel does general-purpose computing. If you're going to build a real-time kernel, you're going to build it because you have, something that is going to be dedicated to do something or other. So a lot of stuff's going to break, but you don't care about that because you disabled it anyway. You've thrown it out of the kernel because you don't need to use it. Actually, I'll get to you. Yes, okay, you. Yes, the orange shirt thing. I have not personally. Anybody? Not seeing any hands. So, sir, yes.
One of the techniques was basically harvesting the periodic interrupt in 13, and then in your ISR masking off other services so you can control what the kernel is really doing.
Yes.
I'm wondering if there's a way to do that in a Pi to basically set those interrupt masks so you can say other people are sending things in, but I don't really care about you right now because I'm in control. I want to enable them and disable them.
Yeah, go ahead.
There's a module called Xenomai. So essentially, it's a parallel kernel. You don't have N13 because it's not x86, right? Sure. So you don't have that.
But the equivalent, you're sending in pulses that
you can have an interrupt. You can have an interrupt scheduler running essentially a parallel RTOS at the same time as Linux. So sometimes you can actually communicate to it from Linux. So Xenomai XEN is probably the popular one right now. There's several of them out there. But essentially, they just take the interrupt instead of Linux, and so they run at a higher priority than Linux. But you lose the device driver, so you have to start programming essentially bare metal inside that ISR.
It's kind of interesting because it must be at the kernel level, the kernel layer then.
mean, it's below. I mean, it's taking the interrupt before the kernel would get it.
Oh, okay. Because I was wondering how could it be faster than the kernel, but,
And because it interrupts the kernel at any time. So, but the thing is like, you're not changing the drivers in the kernel to be preemptible.
mhm.
You can't mess with any of the operating system state within there.
That's what I was kind of worried about, yeah.
So it has another communication mechanism to talk to the.
What's the name of that one?
Then on my XENOMAI.
Yeah, I've heard of it, I've just never played with it. Yes, sir.
So the difference in the real-time kernel is just in the scheduling of how you choose what's on the CPU and just make sure it has the timing requirements?
Yeah, it's the core of it because it has the preemptive, and then it has, like I said, a lot of the services that are not included. Anything else? Well, one more.
Has anybody used the multi-core package to be able to basically split the thing in half, have a preemptive running on one and a non-preemptive running on a couple of the other cores and setting the infinity one way or the other?
Yes. So, not above this talk, but in general terms, both RTMS and the evil VxWorks one that costs, I mean, to show you the difference, RTMS is freeze and beer, freeze and freedom. If you go to Wind River and say, I want an RTX license, they'll say, absolutely great. Here, give me $10,000. And that does not include support, by the way. So, the other beautiful thing about RTMS is you have the available the source code. So let's say you find a feature in VxWorks for your application. You say, hey, Wind River, I think I found a bug in your code. They say, great, give us $50,000 for support. So both VxWorks and RTMS, you could actually assign cores to your tasks. Now it gets kind of tricky because it's not a linear relationship. You think if you have 4 cores and you have 4 processes running at the same time, that's good. But remember, each individual cores have shared resources. So eventually you have diminishing returns, especially with the new stuff, which has like 8 and cores and stuff. Yes?
So with RTMS, when you're using it on the Pi, is the reason the network doesn't work because the USB bus isn't working? Can you use any USB, or is it just because it can't handle the transition between USB?
I think it's just a bug. It hasn't been properly ported. I do know that it supports USB. So I think it's just more of there's some bug that they need to work out. But again, because it's an open source project, it's eventually going to get solved. So if I did this talk next year, I wouldn't be talking about that because it's a very active community, by the way. Yes, sir.
So, quadcopters are running off microcontrollers for the most part.
Right.
If you throw everything out of your Linux system for the Raspberry Pi, what is left of Linux that you really care about, and not just throw out the OS and just go with a microcontroller or some other system where you've written all the real-time portions yourself?
Right. So somebody in my group, in my lug, named Dave, he would absolutely agree with you. Because he's a pick guy. I mean, he's like a really pick guy. The thing about that is, yes, what is left is basically the real-time scheduling kernel for your applications. Yes, you could go microcontroller route. That's my personal preference, actually, to go that way. But because Raspberry Pi is an educational device, that, it'd be good for teach kids that, pick controllers and that kind of a thing. But if you could, especially with limited resources with schools, if you could give them Raspberry Pi and just do some software tweaks, and you could actually run a quad core or a quadcopter, that's it. But yeah, I mean, yes.
Just hearing all this pieces that you have to put together, is there projects out there where you're trying to make a Raspberry Pi that comes fully ready to go?
As far as I know, no.
Sounds like a natural progression.
Yeah, I mean, to be honest, a lot of those people would rather probably just do Arduino or maybe a BeagleBoard Black. But again, the goal of my talk is sort of do like a hacker thing, you know, get something that's not normally a good fit and see if you can make it a good fit just because it's fun. Yes.
So under platform Linux in general, by throwing everything out, do you mean like your OS install will be basically the binary you want to run is just stuck as sbin/init, and you just have like libc and links?
Yeah, I mean, yeah, basically all the module stuff, all the device driver stuff that you don't have, just get rid of it.
Like you don't have anything else other than your binary as sbin/init at this point?
Yeah, I mean, if that's what, I mean, again, it sort of depends on your project, because yes, you may say, I have a real-time kernel, but I also have a camera. So I'm going to need to take those device drivers for that. Yes?
Back to actually what that when you use the microcontroller, what is the relationship between the signal you give the microcontroller and then the signal into it?
Oh,
I need this many of your pulses.
yeah, so it depends on your it depends on your stepper motor, but you have to look at your data spec. But all those, like I said, are pulse driven, and they have your motor would have requirements on that. So what you need to do is look at your stepper motor, and then.
So why does the microcontroller matter rather than you just sending the signal from the I/O?
You could do that if you want to bypass Raspberry Pi.
No, I want to understand what is the purpose. It's like you give it a bulk command. I need so many angles. Okay.
Yeah.
So what is the signal you send to request the answer?
Oh, it depends on usually your stepper motor. Some of them have microcontrollers on them, so if you like do a serial link, so you just basically send. It depends on the motor. You could send it so many pulses that go these many steps. You could send it. Some of them, like I said, have some logic to them. You could actually give it like a 5 and figure it out. So I think that is it. Thank you for attending my talk. Thank you for coming to SCaLE. I hope I see you all next year. Well, yes.
One thing you work in some equipment you just cannot share what it is.
Well, one of them was the F-22.
Yeah, okay. Do you know anybody working on SCaLE?
Okay, SCaLE Linux.
SCaLE.
Oh, do I know somebody personally? No. But I've heard of people that work in.
That is actually
Yeah. I just don't know anybody off the top of my head. But again, do the Google search and probably find.
Well, yeah, but there's only one open SCaLE which is kind of dead.
Oh, really? It's a shame, actually.
Yeah.
Can I just quickly ask,
Yes.
the slides, are you going to have them somewhere? I don't even know if SCaLE puts them. I've never.
Oh, yes. So this SCaLE has my slides, and they should be available. If not now, really soon.
So just keep checking the SCaLE
Yes.
website. Is that how?
Yes, ma'am.
Okay. I've never shared except I like yours.
Oh, thank you. Oh, I'm honored.
Thank you.
You really build your own kernels. That is awesome.
Yeah, I run Gen 2, so
Oh, you have to.
I don't like Gen kernels. It's too bloated. Have you ever used the Raspberry Pi in your project with the F-22, or you don't want to talk about it?
Oh, no. Usually my stuff is, rad hardened. But I mean, the thing of it is
Do you guys ever use like the RTMS, or do you guys mostly use VxWorks?
we mostly use VxWorks. We do have what's called side projects that use RTMS. Normally because, well, that and it's a classic open source thing. It's like, who are you going to sue kind of a thing.
Yeah.
So if you have this multi-billion-dollar space thing and it crashes, you don't want to go to the general and say, well, we picked the free one. You know, you'd go like, oh, it's those guys. It's Wind River, and they're a publicly traded company.
Yeah, a couple of little bits of feedback to you.
Yes.
You're in the same room. Dan, the guy with SCaLE that goes around in the cart, did a real-time processing on some other little microcontroller, and he did the whole lecture, and at the end he said, well, you have to put an FPGA board on it to do real-time processing.
Oh.
A recommendation for you in terms of that manner, kind of, it went a little bit in that manner. Add bunches to your slides on the RTOS and the real-time embedded stuff, and because that's where it really fits into the Linux and what you're talking about, all that type of stuff. For 2, on the Mars rover, you got the exact example of priority interrupts not working. But the problem was that it's stepper motors. You go bang, 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 bang. You miss one step, it grinds to a halt. VxWorks did not have interrupt priorities in it back in 92, 93
Really?
when that was done. And they had their solution on it was they had the radio working. It worked on the ground, but they didn't test it with the radios.
Oh, and the radio was affecting.
Yeah. So what they did was and they had the interrupt bam, 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 bam going out to the stepper motors. And the radio interrupted and ground to a halt. Their solution was we only put one step out at a time.
Oh, really? Well,
Yes, but it wasn't. They missed up their priority interrupts. It stayed down.
oh, funny. It's interesting.
But excellent thought.
Thank you. Yeah, I mean, it's kind of struggling. It's like, because I mean, I could go really in the weeds in this, but then I want people to gloss over, like, wow, what
Add
the...
in like 4 or 5 slides on real-time Linux display.
Yeah. Thank you for the suggestion.
I was wondering, have you ever heard of a real-time operating system called RTAI?
RTAI. I don't think so.
Oh, okay.
But I'll look it up. I'm really curious.
It's more of a higher level scientific.
Oh, like academic research kind of thing?
Yours is more nuts and bolts, like low level for
I'll take a look at it.
When is it necessary for on a real-time operating system? Is it part of the definition that a user process can preempt the kernel, or is that not necessary?
Well,
Is it just the most common way?
yeah, you have to be very careful with that though.
Yeah.
Because I mean, you don't want to have priority inversion. I mean, you don't want somebody, if a user is going to push a button to put some command,
Yeah.
There's probably other things that need to happen.
What was the repeatability schedule from the RTEMS of Raspberry Pi? What was the minimum latency?
Oh.
What was the?
So I got a Raspberry Pi, installed RTMS on it on my workbench, and then I connected the AD8950 to it, and then I just hooked up an oscilloscope and looked at the pulses.
Yeah, but what's the minimum time frame that you got from the?
Oh, I can't remember. It was.
There's the real-time
It
requirement.
was yeah.
What's the minimum?
Because the real-time requirement is based on your system. I think I was seeing like 900 nanoseconds.
You got that from Raspberry Pi.
Well, processing the signal to the pin, and then seeing the output going out.
So it's just 900 milliseconds.
Yeah. I think that was right. I should have had a screenshot actually.
Can you fit on the Raspberry Pi? This is my question. What's the time frame between the 2 real-time events happening, scheduling? What's the?
Well, it depends on your system, right?
Okay.
So let's say you're doing a tank.
Yeah.
Your tank is going to have different timing requirements than an airplane.
I understand, but what are yours? That's the question.
My personal ones at my work?
For this nursery.
Oh, I was just messing around. So I was just doing a measurement. I was actually not building anything. I was just basically saying, could I do it? Could I hook a real-time clock? Could do these things? So I wasn't actually building something. Like, if I was, some people in my lug want to do like a quad core. So obviously, you have stabilization, and you definitely want to, you're very concerned your motor speed because you don't want to have an imbalance so it just depends on your system.
Yeah, no.
But I was just messing.
Okay. Yeah, I need the interest to talk.
Yeah.
But why I'm here because we use RTEMS I work for Slack.
Ah. Sure.
And they use RTEMS basically on the controllers. They have DME-based CPUs, right?
Uh-huh.
CPUs, and they use RTEMS.
They like it?
It works.
It works, sure. That's actually good praise, actually. It works.
And it fits their requirements, basically. I think for now it's 120 hertz they need, basically. So.
Okay. I mean, you know what they're running it?
Operating maximum is 120 hertz.
Ah, cool. You know what they're running it on? Like what CPU they're running it on?
NVMe 6100, it's Motorola CPU.
Well, still though. Sure, like this SBC kind of a thing.
Maybe.
Oh, okay. Cool.